Good morning everyone, my name is Zikriadi Tiara. In this opportunity, I would like to present a research article entitled Efficient Hydrogen Peroxide Generation from Organic Matter in Bioelectrochemical System. Don't forget to like, subscribe and leave a comment if you have any question. The content of this presentation are Introduction, Experimental Section, Result and Discussion, and Conclusion. Introduction. H2O2 or hydrogen peroxide is an oxidator with numerous applications, for example, pulp, paper bleaching, chemical syntheses, and textile bleaching. This compound is produced through an anthraquinone oxidation process, as you can see at the right picture, that is an anthraquinone compound. The syntheses of hydrogen peroxide will be explained in the next slide. Theoretically, it is possible to develop BES for hydrogen peroxide production from wastewater by coupling anodic oxidation wastewater organic to cathodic produce hydrogen peroxide. This production does not require any expensive catalyst such as platinum. Moreover, carbon can be used as catalyst for the production of hydrogen peroxide. MFC for hydrogen peroxide production is an exergonic reaction with the value of Gibbs free energy is -431.83 kilojoules per mole, which makes this reaction is spontaneous. The aims of this research is to investigate the potential of a system by demonstrating the working principle and assessing its performance. As you can see in this slide, various methods for the production of hydrogen peroxide. For example, MFC, MEC, homogeneous BEF, heterogeneous BEF, in situ BES, and ex situ BES. Generally, the reaction of the BES is the same. On the anodic side, the COD from wastewater will react with anode membrane and produce proton. This proton will transfer to cathode membrane and react with oxygen and produce hydrogen peroxide. Experimental section. The experimental section in this presentation are electrochemical cell, startup and operation, and experimental procedures and calculation. For the electrochemical cell, the experimental runs were performed in an electrochemical cell that consisted of two parallel perspex frames, with internal dimensions 14 by 12 by 2 cm, separated by a cation exchange membrane. These membrane and frames created an anode and a cathode chamber, both with an empty bed volume of 336 milliliters. The anode side of the electrochemical cell was separated from the outside by a perspex plate. The anode chamber filled with granular graphite, with diameter ranging from 2 to 6 millimeters, as the anode material. The stainless steel frame left an exposed, projected cathode surface area of 185 square centimeters. Electrode chambers were equipped with an AGTAGCL reference electrode. The electrochemical cell was connected to a potentiostat. The cathode side was separated with carbon cloth gas diffusion electrode. The gas diffusion cathode was connected, through a stainless steel frame, current collector with internal dimensions 13.6 by 13.6 by 0.1 centimeters. Anode and cathode potential were continuously monitored, with a multi-channel data acquisition unit. All electrode potentials are reported versus normal hydrogen electrode. For the startup and operation, the anode chamber of the electrochemical cell was fed continuously at 1 milliliter per minute with an autoclaved feed. pH 7 buffer contained 1.0 gram per liter of sodium acetate, 18 grams per liter of disodium phosphate, 9 grams per liter of potassium phosphate, 0.1 gram per liter of ammonium chloride, 0.5 gram per liter of sodium chloride, 0.1 gram per liter of magnesium sulfate heptahydrate, 0.015 gram per liter calcium chloride heptahydrate, and 1 milliliter per liter trace nutrient solution, dissolve in DI water. The anode chamber was continuously mixed by recycling its contents at about 100 milliliters per minute. The anode chamber was inoculated with a microbial consortium taken from an MFC performing carbon and nitrogen removal. The anode potential was controlled at -0.2 volt. The cathode chamber was filled with a 2.9 gram per liter sodium chloride solution 50 millimolar, and operated in batch mode. The electrochemical cell was left in open circuit for 4 days until the anode potential decreased to -0.27 volt. This treatment could lead the microbial to adapt in the system before the electrochemical process started. BES was operated at a constant applied cell voltage of 0.5 volt, for example, an applied voltage level at which high current densities could be maintained at a sufficiently low energy input. During the following days, the current production increased and stabilized after 2 weeks of operation. All experiments were performed at room temperature at 22 degrees Celsius. For the experimental procedures and calculations, the BES was subjected to an applied current scan. The cathode chamber of the electrochemical cell was rinsed 2 times and subsequently filled with a 50 millimolar sodium chloride solution. The system was first left in open circuit for 10 minutes to establish equilibrium conditions. A scan rate of 0.1 milliampere per second until the applied cell voltage reached 0.5 volt. Cell voltage and electrode potentials were monitored during the applied current scan. In addition to the applied current scan, BES was assessed during 8 hours experimental runs at an applied voltage of 0.5 volt. Cathode chamber of the electrochemical cell was rinsed 2 times and subsequently filled with a 50 millimolar sodium chloride solution. During the experimental runs, anodic influent and effluent acetate concentrations and cathodic hydrogen peroxide concentration and pH were determined at 2 hours intervals. Acetate concentrations were determined using high-performance liquid chromatography. Hydrogen peroxide concentrations were spectrophotometrically determined using the vanadate method. pH and conductivity were measured using a handheld meter. The Coulombic efficiency is calculated by the charge of production divided by charge of consumption multiplied by 100%. Result and discussion. Now, if we look at Figure 2, we can see that the anode potential at open circuit was measured at -0.24 volt, which is quite close to the theoretical potential for acetate oxidation, calculated at -0.28 volt at a pH of 7, as shown in Figure 1. On the other hand, the cathode potential at open circuit was 0.10 volt, which experienced a significant potential loss of about 0.18 volt when compared to the standard potential for hydrogen peroxide formation, which is 0.28 volt at pH 7, also indicated in Figure 1. The open circuit voltage we obtained was 0.34 volt, which is a positive value. This means that, theoretically, the system has the potential to deliver a net power output. As we increased the current density during the applied current scan, the cell voltage began to decrease but stayed positive until the current density reached 0.16 milliampere per centimeter square. At that point, the system reached short-circuit conditions, where the cell voltage dropped to 0 volt. From Figure 2, we can see that at low current levels, it's possible to produce hydrogen peroxide while also generating electricity. However, the hydrogen peroxide production rate is quite slow under these conditions. The figure also shows that by applying a small amount of electrical energy, specifically a negative voltage, we can significantly speed up hydrogen peroxide production. Moving to Figure 3, we tested the system at a voltage of 0.5 volt over an 8-hour period, and the results showed an average current density of 0.53 plus or minus 0.07 milliampere per centimeter square, which closely matches the values predicted by our earlier tests in Figure 2. At the start of the experiment, the hydrogen peroxide concentration was 0 millimeters or 0.8%. After 8 hours, it increased to 38 plus or minus 3.9 millimeters or 0.13 plus or minus 0.01%. This corresponds to a volumetric hydrogen peroxide production rate of 1.9 plus or minus 0.2 kilograms hydrogen peroxide per cubic meter per day. Figure 3 presents the results of our experiment, where we tracked 3 key parameters: first, acetate consumption; second, charge production; and third, hydrogen peroxide production, all expressed as charge. We found that the amount of acetate consumed matched the charge produced throughout the experiment, indicating that our system had a very high efficiency of approximately 98.4% in converting acetate to electrons after 8 hours. However, we also observed that the production of hydrogen peroxide did not fully align with the charge, particularly later in the experiment. This discrepancy reduced the efficiency of converting electrons to hydrogen peroxide to 84.4%. Overall, after 8 hours, the system achieved an efficiency of 83.1% in converting acetate to hydrogen peroxide. At a voltage of 0.5 volt and an efficiency of 84.4%, our system utilized approximately 0.93 kilowatt-hours to produce 1 kilogram of hydrogen peroxide. This is significantly lower than the 4.4 to 8.9 kilowatt-hours required by traditional production methods. This innovative technology has the potential to make a substantial impact on various industries. The global market for hydrogen peroxide is approximately 2.2 million tons, with 50% of it used in pulp and paper bleaching. Notably, this industry also generates wastewater rich in biodegradable materials like acetate. This presents a great opportunity to integrate wastewater treatment with hydrogen peroxide production, ultimately helping to reduce the environmental impact of the industry. To make this system practical, we need to implement some improvements. Currently, the system produces hydrogen peroxide at a low concentration of 0.13%, which is too low for commercial sale but can be used directly on site. For instance, the kraft pulp and paper bleaching process requires a concentration of 2 to 3%. Our experimental runs indicate that there is a decreasing cathodic efficiency at higher hydrogen peroxide concentrations, especially as the experiment progresses. This suggests that hydrogen peroxide is being further reduced to water. Following the reaction, hydrogen peroxide plus 2 proton plus 2 electron will produce 2 moles of water. To achieve the necessary concentration of 2 to 3%, we must focus on improving efficiency. This could involve adding more oxygen or incorporating hydrogen peroxide stabilizers, such as ethylenediamine tetracetic acid or silicate. Additionally, we should investigate whether higher hydrogen peroxide concentrations might damage the materials of the system. Conclusion. In conclusion, hydrogen peroxide can be produced efficiently from acetate in a BES. At an applied voltage of 0.5 volt, the investigated BES produced about 1.9 plus or minus 0.2 kilograms hydrogen peroxide per meter cubic per day at a concentration of 0.13 plus or minus 0.01 weight% and an overall efficiency of 83.1 plus or minus 4.8%. If the hydrogen peroxide concentrations can be improved to about 2 to 3 weight%, this process could have important industrial implications. And the question are, what is the initial open circuit voltage of acetate oxidation? How much hydrogen peroxide is produced for 1 day in this paper? Mention 2 uses of hydrogen peroxide in industrial application. Thank you for your attention. Hope you can get new knowledge from this presentation. Have a nice day.